Welcome back. Let's do some more trig today. Today we're going to take a look at complex roots and we're going to look at powers of complex numbers. This is the why we even started talking about trigonometric form of complex numbers in the first place. This is why it's so handy to know how to write an imaginary or complex number in the form of a trigonometric form so that we can raise something to the 8th power or the 10th power or take the 4th root of it or something like this. So here we go. 6.3 is about, there we go. 6.3 is about powers and roots of complex number. Let's make sure you have your terminology correct first. Hopefully, you know that we talk about, this is a power right here. This is the 4th power is 16. This, however, this is the root, okay? We can say the 3rd root of 27 is, well, one of them is 3. I think you know that. But there's actually 2 more. And how many roots are there? There are 3 roots to that. We're going to talk about how to find the rest of them. For this one, there's 1 solution. For this one, it depends on what root it is. If it's the 3rd root, there's going to be 3 solutions to this. So with roots, there's more than one. A lot of times we just find the real number. And that's what you did in Algebra 2. You just found the real solution. But there are 2 more other roots. If it's the 3rd root, there should be 3 solutions. Now let me talk about why we want to write something in trigonometric form. Suppose I ask you to do negative square root of 3. Got a little issue with, there we go. Internet's being a little sluggish. Forgive the internet right quick. But okay, if we're gonna, can you imagine multiplying that out 8 times? Oh my goodness, 8 times and multiplying and simplifying. Oh, that would be horrible. This is why there is a theorem. A French guy named, I'll write it down. A French guy pronounced de Moivre came up with this theorem. If you have a complex number in trigonometric form, and you want to raise it to a power, then that number to the nth power is r to the n times the cosine of that angle times n, or n theta, theta n, plus I times the sine of n theta or theta n. Those can be written either way. And that is how you find it. Notice that if it's the 3rd power, you would say r to the 3rd and put a 3 there and put a 3 there. The answer to this, we have 1 solution. There is 1 solution to this. We raise something to a power, we get 1 solution. Okay, so let's take a look at using this thing now. Sometimes you'll be given special angles to use it, sometimes not. Let's just do the one I just talked about, negative square root of 3 plus I to the 8th power. Now we're not going to multiply it out 8 times. Oh my goodness, that would be horrible. So the first thing we're going to do is change the complex number to trig form, to trigonometric form. So that's the first thing you're going to do. So let's see. We know how to do this. We've talked about this yesterday. Here is the real part of the of the complex number and the imaginary part of the complex number. It looks like we go negative square root of 3 and then go, what, up 1? It's like a 1 there. Go up to 1, and that is the number we're talking about. So let's put it in trig form. We know that this is negative square root of 3, and this is 1. I think that's a special right triangle. That's going to be 2. Across from the 1 would be 30 degrees. This is a special right triangle. This is easy enough. The r is 2. And the theta, let's see, that's a 30 degrees. So That's going to be what, 150 degrees for theta? How are we doing so far? Let's rewrite this. So we can rewrite this number right here as 2 times the cosine of 150 degrees plus I times the sine of 150 degrees. That is the complex number. Now we're going to raise that to the 8th power. We can now apply de Moivre's theorem by taking that and saying, okay, we take the number to the nth power. Well, let's see, this is my n right here. That's my 8. So we're going to take, what, 2 to the 8th power. We'll figure out what that is in just a minute. Times the cosine of 150 degrees times 8 plus I times the sine of 150 degrees times 8. Okay. Okay, so 2 to the 8th power. Grabbing my calculator. 2 raised to the 8th power is 256 times the cosine of 150 times 8. 150 times 8 is 1,200 plus I times the sine of 1,200 degrees. Okay, did a parenthesis around that. All right. Next thing we're going to do is take this large number right here, and I want to change it to get a number between 0 and 360 degrees. Remember, we called those coterminal angles. So let's see if we can get that to a coterminal angle. Do you remember how to do that? All we do is take 1,200 and we subtract 360, subtract 360, subtract 360 again. What do we get? 120. Okay, so that's 120. I didn't just miss that. I actually changed to a coterminal angle. I'll write that out beside it. Oops, that's a parenthesis. Okay, get coterminal angle. So we've got a coterminal angle. Now we're just going to change it back, the directions. Notice our original problem was not in trigonometric form, so we need to write our final answer in a plus bi form, standard form. So let's see. We now have 120 degrees. That's 120 degrees. That leaves, what, 60 degrees right there? That's a special right triangle. 2, 1, square root of 3. Let's see if we can fill in what this is and what this is, and then we'll distribute and go from there. So that's 256 times the cosine of 120. Let's see, cosine adjacent over hypotenuse. Oh, that's going to be a negative there. That's negative 1/2 over 2, so negative 1 over 2. Plus I times the sine of 120, square root of 3 over 2. So far, so good. Now we're going to distribute the 256 to both of those. Half of 256, half of 256, negative. It's going to be a negative 128. Plus half of that again is what, 128 again? So 128 I square root of 3. Usually put the I there instead of the end. It's not wrong if you put it at the end. We just don't want to make it sure it's not under the radical. There you have it. Look what we just did. That really is a whole lot less time than multiplying that out 8 times and simplifying it. Much easier. We thank you, Mr. de Moivre, for figuring that out for us. So that's how you raise something to a power. You raise something to a power, you get one solution. We showed you how to do it. Change it to trig form. Use, if it's a special right triangle, we'll use drawing it out, figuring out the angles, so on and so forth, multiplying, get a coterminal angle, and go from there. Okay, let's take a look at the complex root theorem. Okay, the complex root theorem. Okay, so now we're finding roots instead of raising it to a power. So just right quick, n in this problem is going to be a positive integer in this theorem. Z is going to be our complex number in trig form. It's going to be our r times cosine of theta plus I sine theta. That's our complex number. Then, according to this theorem, the n distinct roots, let's see if I can spell that, distinct roots, and that means different. There are n different roots. Distinct roots are z to the 1 over n is equal to r to the 1 over n times the cosine. This is going to look really scary at first, but don't worry, we'll figure it out. Of theta plus 360 degrees k all over n plus I sine of theta plus 360 degrees k over n. Close, close. My plus sign almost didn't come out there. Let me make sure that plus sign. Plus I times the sine of that. Okay, this looks kind of familiar, right? Plus 360k keeps giving me all the solutions divided by n. So you can see that instead of raising it to the nth power, we do the nth root of it. Instead of multiplying by n, we divide by n. But there are more solutions that come out of it, and this is how we get the other solutions. And this is going to be for k equal to, so this is going to be for k equal to 0. We start out 0, 1, 2, and go all the way up to n minus 1. And that'll give us n roots because we count 0 as a root, and that'll give us exactly n roots. Okay, that's how we raise it to a root. That is our theorem that we're going to use. Now, I need to point out, these aren't always in degrees, okay? So if it's not in degrees, then what we're going to change here is only right there. We're going to put a 2 pi instead of 360, and we're going to put a 2 pi for radians instead of 360. Everything else will be just the same. Okay, we're ready to go for this one. So for this example, example 2 here is find the fourth roots of -8 plus 8i square root of 3. Okay, find the fourth roots. There should be 4 of them. Okay, we should have 4 answers. In fact, we'll go 0, 1, 2, and 3. 0, 1, 2, and 3 will give us 4 answers. Okay, so the fourth root, that's going to make our n be a 4. The fourth root, that's going to make our n be a 4. So first thing we're going to do is get in trig form. I'll get it in trig form, just like we did before. Okay, here's a real number line. Here's the imaginary. Let's see, we have -8. And then go up, what, 8 square root of 3? There it is. So this is 8 square root of 3, and this is -8. Okay, now I don't know if you notice the pattern here, but this is a 1 to the square root of 2 to 2. This is going to be a special one. This is going to be 16. Okay, and this angle right here, let's see, across from a square root of 3 is a 60-degree angle, which makes this 120 degrees. So we've got our r and we've got our theta. Our r is 16, that's our r. R is 16, and our theta is 120 degrees. So in trigonometric form, our z is 16 times the cosine of 120 degrees plus I times the sine of 120 degrees. Now we want the fourth roots of this. So n equals 4. So let's see if we can do our pattern. So we want z to the 1/4. Okay. Okay, z to the 1/4. That's our fourth roots of this. According to this theorem, it's r to the 1/4. So r right there is 16. 16 to the 1/4, or the fourth root of 16, times, let's see, the cosine of, what we do here is do 120 degrees plus 360k, all divided by n. And n is the fourth root, so it's 4. And then plus I times the sine of that same angle. 120 degrees plus 360 degrees k, all over 4. Close that, close that. Okay, let's simplify this a little bit. I think we need to simplify that. 16 to the 1/4 power. If you don't remember how to do that, you just put it on your calculator like this. 16 raised to the 1 divided by 4 gives us 2. This part is 2. Times cosine of 120 divided by 4 is 30 degrees. Plus 360 divided by 4 is 90 degrees. Plus I times sine of the same thing, 30 degrees plus 90 degrees k. All right, so far so good. Now what do we let k be? And this is going to be for k equals 0, 1, 2, 3. Stop. 1, 2, 3, 4 answers. It's a fourth root. There should be 4 answers. Always start at 0. So we're going to let k equal 0, write it down. K equal 1, write it down, so on and so forth. So let's do that. Let's let k equal 0. Then our complex number, we'll say z sub 1. We'll say z sub 0. I think that makes more sense. Is going to be 2 times the cosine of, let's see, 30 degrees plus, we're letting that be 0, so it's just 30 degrees. Plus I times the sine of 30 degrees. There's the first answer. Well, what you're going to have to do is change it back. You can change it back now, or you can change it back later. Might as well change it back to a plus bi form. Let's see, a quick little 30-degree angle in a right triangle. That's 1, 2, square root of 3. The cosine of 30 is square root of 3 over 2. Plus I times the sine of 30 is 1/2. Distribute the 2. 2 times up, 2 is going to cancel. We're going to get square root of 3 plus I. There's one solution. There's one solution for the fourth roots of that. Okay, let's try another one. I always kind of like to draw a little line here. Let's let k equal 1. Then z sub 1 is equal to, let's see, 2 times the cosine of, now k is equal to 1. K is equal to 1, that's going to be 90 plus 30 is what, 120? 120 degrees plus I times the sine of 120 degrees. Okay, let's see, 120 degrees. It's going to leave, what, 60 here? That's going to be square root of 3, 2, negative 1. Okay, so here we go. So that's going to be 2 times the cosine of 120 is, what, negative 1/2? Plus I times the sine of 120, square root of 3 over 2. Distribute your 2 to both of those, and it looks like we're going to get, what, negative 1 plus square root of 3i, or I squared of 3 is the way the book will write it. There's our second root. Remember, we should get 4 answers for the fourth root. Okay, I think I got room for another one here. Let's let k equal 2. Z is equal to 2 times, hopefully you'll see a pattern. Each time I'm just adding 90. So if I let k equal 2, that's 180, and 30 is 210. But we can just add 90 to that, and that's going to be 210. We're just adding 90 each time. Adding 90 each time. So cosine of 120 plus 90 is what, 210? Plus I times the sine of 210. Change it back to a plus bi form. Let's see, 210. let's see, 180, 210. They differ by 30. That's going to be -1, 2, and negative square root of 3. Okay, hopefully you'll notice kind of a pattern here. Cosine is negative square root of 3 over 2 for 210. Plus I times the sine of 210. Let's see, sine is going to be -1/2. So our next answer, distribute the 2. We get what? Negative square root of 3 minus I. Hopefully you're starting to see a pattern here because there is a pattern. We've got one more. Let's let k equal 3 to get our last answer. If k equals 3, all we have to do is add 90 to that last one. So let's let k equal 3 and add 90. So this is subscript 2, and this is z sub 3. So that's 2 times the cosine. Add 90 to that, and that's going to be 300 plus I times the sine of 300. And that's going to be, let's see, 300. That's going to 300 degrees is going to leave 60. That's going to be what? Across from the 30 is 1, negative square root of 3, and 2. So let's see what we have here. So that's 2. The cosine of 300, cosine would be 1/2, positive 1/2. Plus I times the sine of 300 would be negative square root of 3 over 2. And distribute, and that's going to be what? 1, distribute your 2, the 2's will cancel, minus I times the square root of 3. And there's our last root. So there's our 4 solutions. Let me write them down. I want to show you something about these. Our 4 roots were square root of 3 plus I, -1 plus I square root of 3, negative square root of 3, minus I, and 1 minus I square root of 3. Okay, what's really cool about this is if you were to graph these. Okay, let's see. Let's go out to 2. This is the real number line. This is the imaginary number line. Go to about 2. What is that? That's 1.7 is the square root of 3. So if I go out to 2 in each direction, that's -2. I should be okay. Okay, so let's graph this first one. This first one is positive 1.7, approximately 1.7 plus 1I. It's right there. This one is -1, positive on the imaginary 1.7. This one is -3, negative square root of 3, which is -1.7, down 1. And the last one is +1 and down 1.7 on the imaginary axis. If you were to graph this and graph it to scale, you'll find out that that's going to be a regular polygon every time. I'm told that it's really cool because all of these would be the same length, okay? All of these would be the same length. That this is really, it's why our electronics works. These imaginary numbers, they actually found a use for it in electronics. Isn't that beautiful? For electronic stuff, you'll have to go to another course, but not this one. So that's the way this works. If it happens to be the 6th root, you would have 6, and when you grafted them, they would make a perfect hexagon on there, on the graph. It's really cool. It's really cool to take a look at the graph. You're not going to be asked to graph them today, but just wanted to show you that. Okay, third one. I'm not going to work all the way through this, but I want to show you what to do on something like this. Solve x to the 6th equals 1. Now, I know you're thinking, well, that answer is just 1 or -1. But actually, remember, there are 6 solutions to this because when I want to solve for x, I have to raise this to the 1/6 power. there should be 6 solutions to this. So let me first write this 1 as a complex number. 1 plus 0i, and that's going to give me, we want to the 1/6 power. Well, let's see. Oh, this is crazy. So that's 1 on the real number line. On the imaginary 0, that's right here. That's easy enough to find the angle because the angle's 0. The r is 1. So we could rewrite this in complex number form as 1 is the length of my r times cosine of 0 plus I times the sine of 0. And now if I want the 6th roots of it, okay, if I want all 6th roots of that number, if I wanted all 6th roots of that number, then we would have to apply the theorem, dot, dot, dot. Instead of 0, you're going to say 0 plus 360k, all divided by, was there 6 roots? Yeah, 6 divided by 6, and so on and so forth. But it's nice to start off with a 0 right there. And that's how you find your 6 roots. 1 to the 1/6 power, and so on and so forth. Work the problem. I want to tell you that there were actually 6 answers to that. In Algebra 2, a lot of times you just got 1 and -1. You've only found 2 of the solutions. There are 6 solutions. You get to find the other ones because they're all imaginary. There are 6 solutions. 1 and -1 are just the real number solutions that you found. There are 6 solutions to that, and that's how you go about finding 2 of them, and then you can find the other 4 using this new complex root theorem. Okay, I hope you got something out of that today. So we're finding roots and powers of complex numbers. We got to get them in trig form to do it. Your assignment for this section is in 6.3 of Dougal-Polsky, and the white and the blue are actually the same today. They are problems 3, 5, 15, 19, 23, 25, 29, 41, and 45. Now the yellow book is different. They're going to be 5, 7, 17, 21, 25, 27, 31, 43, and 47. All right. I hope you had some fun playing with your complex numbers or your imaginary number friends today. If you have any questions, don't forget to contact me through my email, or you can contact me through a Mind app and let me know you have some questions. I hope you have a great day. Thank you, and bye-bye.